Welcome in Dark Core. What we see in the sky is just the tip of the iceberg: the sun, the moon, stars, planets, and galaxies. All of this visible universe makes up only 5% of its total composition. But what lies hidden in the remaining 95%? Today, the vast majority of scientists agree that most of our universe consists of dark matter and dark energy, two forces that cannot be seen or touched, yet without them the cosmos itself could not exist. One of them acts like cosmic glue, holding galaxies together and preventing them from falling apart. The other, on the contrary, stretches space itself, causing galaxies to rush away from each other at ever-increasing speeds, sometimes even faster than the speed of light. But if these forces are invisible, how can we study them? In 2011, the European Space Agency decided to approach the problem differently. Instead of looking for the forces themselves, they would study what these forces leave behind. If galaxies cluster in one place, dark matter is likely at work. If they rapidly scatter, this could be a sign of dark energy. To test this, the Euclid project was launched, a space telescope designed to create the most detailed three-dimensional map of the universe ever made. This map will help scientists understand how the invisible forces, dark matter and dark energy, shape its structure. In July 2023, Euclid was launched into space, and just recently, it transmitted its first unique images of distant galaxies, nebulae, and superclusters, structures that seem to bear the imprints of these mysterious forces. Right now, these observations are especially important. Recent data from scientists at the Lawrence Berkeley National Laboratory point to something strange in the behavior of dark energy. What if our universe is changing faster than we thought? Euclid is called a cosmic detective because it's not just a space telescope for capturing stunning images of deep space. It's conducting a true investigation into one of the greatest mysteries of the universe, the nature of dark energy and dark matter. As part of its mission, which will continue until 2030, it's set to study 1.5 billion galaxies, peer into the most distant corners of the universe billions of light years away, and in doing so, uncover the true nature of these two mysterious forces. So far, the Euclid telescope has explored only 1% of its target. From March 25 to April 8, 2024, it took 260 images of the southern sky, covering an area 500 times larger than the moon as seen from Earth. From these images, scientists created a mosaic including millions of stars and galaxies. And this is just the beginning of its mission. Let's begin with a photograph of the most massive structure known in the observable universe. Scientists have dubbed this image a revolution in astronomy. It captures the Perseus cluster of galaxies. 1,000 galaxies belonging to the Perseus cluster and over 100,000 additional galaxies in the background. Many of these faint galaxies had never been seen before. Some are so distant that their light took 10 billion years to reach us. This enormous cluster, located 240 million light-years away, could not exist without dark matter. According to scientists, the visible mass, stars, gas, and dust is simply not enough to hold everything together through gravity. It is the invisible dark matter that acts as a glue, keeping the galaxies from flying apart. One of Euclid's key tasks is also to study how dark matter and dark energy influence the shape and movement of galaxies. These invisible forces directly affect how galaxies appear and how they evolve over time. Dark matter is like an invisible framework. It pulls in ordinary matter, stars, gas, and dust, and helps galaxies hold themselves together. Imagine it as a kind of gravitational glue, keeping the stars within a galaxy. Without this glue, everything would just scatter into space. So the more dark matter there is, the denser and more stable a galaxy becomes. Dark energy, on the other hand, operates on a larger scale and does the exact opposite. It pushes galaxies apart, expanding the universe. It influences how quickly galaxies move away from each other, how often they collide and merge, and the conditions in which they continue to exist together. These two forces, one pulling and the other pushing, create the universe's unique cosmic pattern, determining what galaxies will look like: compact, dispersed, or vast and dense. That's why it's fitting that one of the first galaxies observed by Euclid was nicknamed the Hidden Galaxy or Invisible Galaxy, also known as IC 342, which is also considered a twin of our Milky Way galaxy. IC 342 has a shape typical for most galaxies, a spiral. But galaxies weren't always like this. In the early universe, most galaxies were small and irregularly shaped because they formed in a very different, much hotter and denser cosmic environment than we see today. This made their formation chaotic. Gas and dust collapsing under gravity couldn't come together evenly, which is why the first generation of galaxies looked very different. They became the foundation, the building blocks of the formation of larger and more orderly systems like modern spiral galaxies. Though such irregular galaxies are extremely rare today, they are still occasionally found even relatively close to us. This is a galaxy called NGC 6822, and it became the first galaxy with an irregular shape observed by Euclid. It's located just 1.6 million light-years from Earth, and is a member of the same galaxy group as the Milky Way. The last time scientists had a chance to observe it was through images from the James Webb Space Telescope, but those pictures don't compare to the ones captured by our cosmic detective. In these photos, you can clearly see the huge difference in which Euclid surpasses its cosmic colleague in both object detail and in color resolution. Thanks to its infrared instrument and wide view range, scientists have already identified in this image many globular clusters, ancient star formations containing thousands of stars held together by gravity. It also highlights the most active regions of the cluster, known as H2 regions, where stars are born regularly. These star groupings also exist in the Milky Way. Euclid took a stunning image of a cluster called NGC 6397, located 7,800 light-years from Earth. Observing these structures in detail is extremely difficult because most of the stars are concentrated near the center, and brighter ones drown out the dimmer ones. NASA's Hubble Space Telescope managed to observe the core of NGC 6397 in detail, but examining the outskirts with Hubble would take a very long time. Euclid, however, can do this in just 1 hour. That's the same amount of time it took Euclid to capture the most detailed image yet of an enormous star-forming region called the Horsehead Nebula. It's located 1,375 light-years from Earth, south of the star Alnitak, the easternmost star in Orion's famous belt. Many telescopes have already photographed the Horsehead Nebula, but none have captured it as clearly and on such a broad scale as Euclid. For example, the James Webb image only captures the top of the nebula's head. Next to that is a Hubble image, which covers a bit more. However, Euclid's image is astonishing, thanks to the amount of detail and scale, showing the entire nebula in full. In this area, scientists will use the data to search for faint and previously unseen planets with a mass of Jupiter in their cosmic infancy, as well as young brown dwarfs and newborn stars. These are valuable to study because everything born in this nebula forms under extremely particular conditions. These conditions are shaped by radiation from the very bright star Sigma Orionis, located above the Horsehead Nebula. This radiation strongly influences the surrounding gas and dust from which stars are formed. In the photo, you can see how the light from Sigma Orionis makes the clouds behind the Horsehead Nebula glow, while the dense clouds forming the head itself block the light coming from behind, making the head appear dark. The amazing capabilities of the Euclid telescope began to reveal themselves back in September 2023 during its initial test runs. It sent just a few images to Earth at that time, but among them, scientists saw something extraordinary, a perfect Einstein ring. This is a rare cosmic phenomenon where a massive object, like a galaxy, bends the light from a more distant galaxy behind it, forming a ring of captured light. This effect is called strong gravitational lensing and helps scientists peek deeper into the universe. To understand why this is important, imagine a giant lens, but instead of glass, it's gravity doing the work. Any massive object, like a galaxy or cluster of galaxies, has a gravity that wraps the space around it. Light passing through this warped space bends just as rays do when going through a magnifying glass. Thanks to this effect, we can see objects that would otherwise remain hidden. Distant galaxies that would normally be too faint become brighter and sometimes even appear larger. Occasionally, the gravitational lens is so precise that the light bends into a perfect ring, exactly as a phenomenon captured by Euclid. In this image, you can see how the galaxy NGC 6505, located 590 million light-years from Earth, bends the light of another, more distant galaxy 4.42 billion light-years away. The gravity of NGC 6505 distorted the incoming light into a nearly perfect ring encircling the galaxy. Among the data recently received from Euclid, scientists discovered 500 new examples of gravitational lensing, where one galaxy bends and amplifies the light of another. It's expected that by the end of the mission in 2030, this number will exceed 100,000, 100 times more than we currently know of. Meanwhile, 2,000 scientists from around the world participating in the Euclid project will analyze the data to unravel the universe's biggest mystery, the nature of dark energy and dark matter. But even now, the research results on this invisible force are taking a rather disturbing turn. A group of scientists from the Lawrence Berkeley National Laboratory has made a fresh discovery that could upend our understanding of the universe's future. Their research suggests that dark energy is beginning to become unstable. Dark energy is losing power. The universe continues to expand. Galaxies are moving away from each other, and space itself is growing like a stretching fabric. For a long time, scientists believed this expansion would never stop, that one day the stars would go out, matter would disperse, and a cold, empty universe would remain, the so-called Big Freeze. Until recently, hardly anyone doubted this. After all, dark energy, which stretches space itself, seems incredibly stable. Powerful, so powerful in fact that it appeared capable of bypassing the physical laws we're used to. One of its core principles: the farther apart objects are, the faster the space between them expands. Galaxies in the Virgo cluster, which is about 50 million light-years away, are receding from us at 745 meters per second. Meanwhile, galaxies in the Coma cluster, nearly 6 times farther away, are moving away at over 4,350 meters per second. The farther they are, the faster they move. At distances of around 14 to 15 billion light-year, the expansion of space surpasses the speed of light. Does it sound like a violation of the laws of physics? Let's not jump to conclusions just yet. Nothing can move faster than the speed of light, but only within space. If space itself is expanding, those rules don't apply. Imagine a football field. The ball is a beam of light, the goal is our Earth, and the field is space. The ball rolls toward the goal at the speed of light, just over 186,000 meters per second, but the field itself is stretching and doing so faster than the ball can roll, meaning it never reaches a goal. It's the same with distant galaxies. The distance of them increases faster than light can travel. They simply disappear beyond the horizon of the observable universe. This immense cosmic force seemed destined to bring about the cold death of the universe, but recent research suggests a completely different outcome might be on the table. Enter the Dark Energy Spectroscopic Instrument, DESI, a scientific device located at the Lawrence Berkeley National Laboratory. It's equipped with 5,000 robotic fiber optic telescopes that study millions of galaxies each night. Thanks to its data, scientists have created the most detailed 3D map of the universe yet, covering 15 million galaxies and 11 billion years of cosmic history. On March the 19th, 2025, the DESI collaboration released findings showing that dark energy reached its peak strength when the universe was 9.6 billion years old, about 70% of its current age. Since then, its influence has gradually weakened, and it's now about 10% less than it was at that peak. This means that while expansion is still accelerating, dark energy is slowly easing off the gas. If dark energy continues to weaken, something truly unexpected could happen. Instead of remaining a positive force accelerating expansion, it could become negative. Over time, its influence would then reverse, and the universe would begin to contract. Galaxies would start drawing closer together, space would collapse, and the universe would end in a big crunch, a mirror image of the Big Bang. If this data is confirmed, it would be one of the most significant discoveries in scientific history. It would suggest that dark energy isn't a constant force, but something far more complex, possibly tied to physical laws we don't yet understand. Current research is still insufficient to say for certain where the universe is headed, but one thing is clear: our usual ideas about its future are already starting to shift. And as scientists try to predict the future of the universe, they are also diving deeper into its past. Not long ago, astronomers managed to capture the universe in its infant stage, its very first moments after coming into existence. New cosmic baby pictures. Using the Atacama Cosmology Telescope, scientists photographed the universe the way it was 380,000 years old. This is one of the earliest observable stages of its existence. Looking further back is no longer possible. The reason is that after the Big Bang, the cosmos was filled with extremely dense plasma, so dense that for several 100,000 years, it couldn't let light pass through. That's why capturing an image of it from an earlier period isn't possible. However, After 380,000 years, the universe's expansion led to the plasma dispersing, and the radiation from the hot gas began to spread through space. From this moment, the universe became transparent, allowing scientists to see what it looked like in its infancy. Before you are chaotic clouds of hydrogen and helium scattered throughout the young cosmos. But this isn't just a sordid gas, it's the building material of the first stars and galaxies. Over time, under the influence of gravity, these clouds began to compress, heat up, and ignite, giving birth to the first stars. We were given a chance to witness the universe taking its first step toward forming the cosmos we're familiar with. And it's a unique opportunity, as this light traveled to us for more than 13 billion years. The signal was so faint that the image had to be taken with a 5-year exposure. 5 years of waiting is a small price to pay for the opportunity to see what the cosmos looked like at the very beginning of its existence. But in addition to this unique image, the Atacama Cosmology Telescope gave scientists another valuable insight: the key parameters of the universe, its size and mass. According to the data, the observable universe stretches nearly 46.5 billion light-years in every direction from us, and its mass is unimaginable. It's equivalent to 2 trillion, a 2 followed by 36 zeros, suns. However, most of this mass is hidden from us. Only 5% consist of ordinary matter, stars, planets, galaxies, and everything we can see. Another 25% is dark matter, an invisible substance whose gravitational pull keeps visible matter together. The remaining 70% is attributed to the main antagonist of dark matter, dark energy, a mysterious force that's been stretching the fabric of space since the birth of the universe. But these hidden forces don't just determine the behavior of the universe as a whole. They also affect the fate of individual galaxies, including our own Milky Way. Thanks to the Gaia Space Telescope, scientists were able to peer into our galaxy's history and discover that the Milky Way has been a true cosmic predator throughout its evolution, devouring other galaxies. Gaia Space Telescope. This is the most detailed map of the Milky Way ever created. On January 15, 2025, it was unveiled by the Gaia mission scientists. To create it, the spacecraft conducted more than 3 trillion observations, studying over 2 billion stars. At the center of the image, you can see a bar. This is where our dormant supermassive black hole, Sagittarius A*, is hidden. But the most fascinating thing is, rather than just 2 familiar spiral arms, Gaia showed that our galaxy has many more, including several secondary branches. We're located in the outer Orion arm, about 26,000 light-years from the center, closer to the lower part of this illustration. But the structure of the Milky Way turned out to be even more complex than we thought. Gaia's data show that in addition to the main spiral arms, our galaxy may contain traces of ancient, long-destroyed structures. Before you is a map of the entire sky of the Milky Way. Scientists believe that the mysterious structures highlighted with blue lines may be remnants of vanished spiral arms. Over time, they were destroyed due to numerous collisions between our galaxy and its neighbors. Essentially, they are the ghosts or fossils of arms that once shaped the face of our galaxy. This tells us that time and again throughout its history, the Milky Way grew thanks to such collisions. One of its victims is the Sagittarius dwarf galaxy, which has collided with the Milky Way at least 3 times, losing stars and gradually disintegrating. In 2018, astronomers found evidence of these kinds of cosmic battles, specifically a group of 30,000 stars moving synchronously in the opposite direction from the 7 million stars surrounding them. These stars are likely a fragment that the Milky Way tore away from another galaxy. A similar galactic collision is occurring 65 million light-years from Earth. In the image, you see galaxies NGC 4568 and NGC 4567 merging into one. This gives us an idea of what may one day happen between the Milky Way and the Andromeda Galaxy, our closest massive neighbor, located 2.5 million light-years from Earth. But as it turns out, it's not only distant galaxies that hold secrets. Among the vast amount of Gaia data, scientists found something astonishing: a sleeping giant. It's located just 2,000 light-years away from us in the constellation Aquila. This giant black hole has a mass 33 times greater than that of our Sun. It's the first instance where a black hole of this size has been discovered within the Milky Way. Its name is Gaia BH3, and here you can see its location on the map of the Milky Way. Typically, the mass of stellar origin black holes in our galaxy is about 10 solar masses. Until recently, the record for mass was held by a black hole estimated to be about 20 times the mass of our Sun. Despite Gaia BH3's immense size, its discovery was an incredible stroke of luck. This is because it belongs to the type of sleeping black holes. Such black holes have consumed everything they could capture with their gravitational field, exhausting all the galactic material from the nearby cosmic kitchen. There's nothing left for it to consume, so it emits no activity. Like Euclid, Gaia has also made a significant contribution to the study of dark matter and dark energy, but Gaia's approach was notably different. With its data, in March 2024, scientists completed work on creating the largest 3D map of the most dangerous objects in the universe. Every tiny point you see is a quasar. These are the blazing centers of active galaxies, powered by a supermassive black hole that feeds on huge amounts of gas. They are the brightest objects in the entire universe. This is due to the vast amount of matter that the black hole cannot consume quickly enough. As a result, an accretion disk forms around it, where the heated plasma accelerates to 80% of the speed of light. This produces a tremendous amount of light radiation. For example, scientists estimate that the luminosity of the closest quasar to us, 3C272, is 25 trillion times brighter than the luminosity of our Sun. This map marks 1,300,000 such objects, serving as visual proof of how dark matter is distributed across the universe. Without its invisible force that can glue regular matter together, these structures simply could not have formed. The Gaia telescope has made a number of astounding discoveries, but its mission recently came to an end. On March the 27th, 2025, it was shut down and began its slow drift towards its final orbit around the Sun. Each discovery brings us closer to unraveling the mysteries of the universe. We still don't know how this cosmic story will end, whether the universe will keep expanding forever or if we'll face a new great cycle. But one thing is clear: the further we look into the past, the better we understand the future. When it comes to dark matter and dark energy, there's more unknown than known. What we do know is that there is some mysterious force at work attracting and holding galaxies together, while dark energy is accelerating the universe at the same time. But neither one of these mysterious particles has been detected. Now, some scientists believe that dark matter might be swirling around the edges of black holes, and other physicists believe that they found dark energy right here on Earth. Some even say dark energy might not be real after all. Could it be true? Get ready to find out the answers to this and more. If physicists had a most wanted list, dark matter would be at the very top. This is because dark matter is a theoretical, invisible material that should be everywhere throughout the cosmos. In fact, just 5% of the cosmos is normal matter, 68% is dark energy, and the remaining 27% is thought to be dark matter. Dark matter and dark energy are the yin and yang of the cosmos. Dark matter produces a gravitational attractive force, while dark energy produces a repulsive force. The mind-blowing thing is that these theoretical particles make up 96% of the universe, and yet we can't see either one. This is because dark matter and dark energy don't produce, absorb, or reflect any light, meaning they have no interaction with the electromagnetic force. So if dark matter is invisible, then how do scientists know it even exists? The only clue we have that dark matter exists at all is because of the gravitational effects it has on celestial objects in the universe, like stars and entire galaxies. Think of dark matter similar to the way you see the wind on trees. You know there's wind because you can see the leaves moving, but you can't see the wind. NASA researchers have observed certain star clusters exerting far more gravity than should be possible based on the amount of baryonic, or visible, matter they contain. NASA claims these observations wouldn't make any sense without dark matter. Now, the idea of dark matter isn't relatively new. In fact, the first clues of its existence came in the 1930s when an astronomer named Fritz Zwicky was looking at a distant swarm of galaxies that made up the Coma Cluster and noticed something very strange. The galaxies were moving fast, so fast that the cluster should fly apart, but they didn't. This led Zwicky to believe there must be some unseen material hiding among the galaxies, holding them together with some gravitational force. In the 1970s, another astronomer made the same observation. Vera Rubin found that stars were swirling around spiral galaxies much faster than expected, and to avoid shredding themselves, there must be some unseen force holding these galaxies together, possibly the gravity from dark matter. From that point on, many researchers became convinced that dark matter does exist, and many different types of particles have been proposed to explain dark matter. But so far, those experiments have only ruled out contenders, and we're still empty-handed on the subject. Now, a new study says that dark matter may not exist at all. In the study, scientists found small discrepancies in the orbital speed of distant stars that show almost no gravitational effects. Basically, the study shows it could be our insufficient understanding of gravity that's behind the gravitational strength of both galaxy clusters and known galaxies, rather than clouds of dark matter. There's something else that might put the brakes on the whole dark matter scenario. Astronomers just discovered a galaxy that has no trace of dark matter, or what we think dark matter is. An international team of astronomers were looking at the galaxy AGC 114905 and took detailed measurements over a course of 40 hours using state-of-the-art telescopes. In fact, what they found was 6 galaxies with little to no dark matter. AGC 114905 is about 250 million light-years away and is classified as an ultra-diffuse dwarf galaxy, referring to its luminosity and not its size, as it's about the same size as our Milky Way galaxy. However, it contains 1,000 times fewer stars. The prevailing idea is that all galaxies, including ultra-diffuse dwarf galaxies, can only exist if they are held together by dark matter. But using the standard way to reveal dark matter, which is by measuring the distance of the gas from the center of the galaxy on its x-axis and the rotation speed of the gas on the y-axis, the team of researchers found that the motions of the gas in AGC 114905 can be explained by normal matter. However, the problem remains that theory predicts there must be dark matter in galaxy AGC 114905, but observations show it just isn't there. There are some possible explanations for the lack of dark matter. One example is that the galaxy could have had its dark matter stripped away by another large nearby galaxy. The problem with this is that there are no nearby galaxies. Another assumption is the estimated angle at which researchers think they are observing the galaxy. Even though this could point to the end of the theory of dark matter, there have been some other new theories that might prove otherwise. The hunt for gravitational waves and ripples in space-time caused by major cosmic cataclysms could help solve another one of the universe's big mysteries called boson clouds, and whether they are actually dark matter. Researchers are now using powerful instruments such as a laser interferometer gravitational wave observatory, the Advanced Virgo detector, and the Kamioka gravitational wave detector to detect gravitational waves up to billions of light-years away to locate potential boson clouds. Boson clouds are made up of ultralight subatomic particles that are almost impossible to detect and have been suggested as a possible source for dark matter. Researchers will try to hunt down these particles by searching for gravitational waves caused by boson clouds circling rapidly spinning black holes. These particles, if they exist, have extremely small mass and rarely interact with other matter, and that is one of the key properties that dark matter seems to have. By searching for these clouds, we might be able to track down the elusive boson particles and possibly crack the code of dark matter. But dark matter, one of the weirdest substances in the universe, just recently became more mysterious. Despite us not detecting it yet, a new study says that dark matter may come from regular matter. An older theory called freeze-out suggests that dark matter formed in the early universe when all particles were smashed together in a hot, dense soup called a thermal bath. The vast majority of these particles started off as dark matter, which was soon destroyed as soon as it came into contact with regular matter, known in cosmology as annihilation. The reverse of this theoretical reaction, in which dark matter replaced more abundant regular matter in the early universe, is called freeze-in. Researchers took this reverse theory to the extreme, suggesting at first that regular matter outweighed dark matter by a lot. However, that began to change rapidly using a theoretical model. When a particle of dark matter came into contact with another particle, it annihilated that particle and split out 2 particles of dark matter. Now, this is similar in the way other fundamental particles such as positrons and electrons annihilate one another to produce 2 photons. However, this model produces dark matter at an exponential rather than gradually slowing or logarithmic rate. If this is indeed a true mechanism, then it offers a solid explanation for the current 6-to-1 ratio of dark matter to regular matter. But that brings a big question. If dark matter converts everything else into more dark matter, does it mean that the universe is doomed to become one big dark matter blob? Because if it continued too long, you'd end up with a universe with a lot more dark matter than our universe itself. However, this new theoretical mechanism only works at an extremely high temperature, as during the beginning of the early universe. As the universe cooled, the reaction ceased, and the amount of dark matter became fixed. So where does dark energy fit in all this? Dark energy wasn't even discovered until 1998. Observations made it clear that the universe was not just growing larger but also at an accelerating rate. All the known matter that we can see, planets, stars, and entire galaxies, should be pulling in on the universe, not pushing outward. In fact, the accelerating expansion of the universe was a huge surprise to scientists. It was then that astrophysicists came up with dark energy to explain the strange behavior of the universe. Filling all of space, dark energy's negative pressures inflating the cosmos like a balloon and interacts very little with gravity. Now, astronomers think they may have just discovered dark energy right here on Earth, by accident. Using method to find dark matter in 2020, physicists utilizing the Xenon 1T facility reported that the experimental dark matter detector picked up a strange signal, possibly hinting at new physics. However, a little time after the experiment, the physicists were now saying that the experiment might have picked up the first direct detection of dark energy, the mysterious force that's accelerating the expansion of the universe. The experiment was essentially a big tank full of liquid xenon, kept deep underground. The idea of the experiment was that if a dark matter particle zipped through the tank, it would excite the xenon atoms to produce a flash of light and free electrons, and a suite of sensors would detect it. But other known particles could have the same effect, so putting the experiment underground helps reduce the probability of unwanted noise. But not all. With this, scientists calculate an expected background level of events, then check if the actual detections are higher than this. When they checked, they were surprised to find an excess of events, 53 to be precise, over the expected background of 232 events. Something strange seemed to be happening. But was it dark matter? The leading candidate at the time was a hypothetical elementary particle called a solar axion, which, as the name suggests, would be produced by the sun. They aren't considered to be a dark matter candidate, but other types of actions are. Finding evidence of these actions would be a major step towards finding the elusive dark matter particle. But after further investigation, it was found that far too many solar actions would be needed to produce the observed signal. It was at this time they suggested a different culprit, a force carrier particle for dark energy. Some astronomers have their doubts and say if it's true that dark energy has been found, it's a stunning discovery, but a lot more need to be verified before coming to this conclusion. Directly detecting dark matter or dark energy will be one of the most important discoveries of all time, but it's no easy feat to find something that's invisible and barely interact with regular matter. By 2025, NASA will launch a new telescope designed to unravel the mystery behind dark matter, the Nancy Grace Roman Telescope. When astrophysicists finally do find dark matter or dark energy, we'll be here to tell you all about it. So make sure to stay tuned here, and thanks for watching Dark Core.